The Nobel Prize in Physics 1978. The Nobel Prize in Physics 1978 was divided. One half awarded to Piotr Leonidovich Kapitsa for his basic inventions and discovery in the area of low-temperature physics, and the other half awarded to Arno Allan Penses and Robert Woodrow Wilson for the discovery of cosmic microwave background radiation. Piotr was born in Russia. He worked in Cambridge for more than 10 years, like assistant director of magnetic research at Cavendish Laboratory. In 1914, he went to a professional visit to the Soviet Union, but wasn't allowed to return to Cambridge, so during World War II, he directed the Department of Oxygen Industry. The first Nobel Prize in this area was given in 1913 to Cameron Wans for his inventions and on the properties of matter at low temperature, which led into to the production of liquid helium. This substance has become one of the most useful means for low temperatures. In 1934, Kapitsa constructs a new device for producing liquid helium. Liquid helium which cooled the gas by periodical expansions. For the first time, a machine had been made which could produce liquid helium in large quantities without previous curing with liquid hydrogen. In 1920, it has been found that when liquid helium was exposed to a temperature less than 2.3 degrees above absolute zero, it has changed into an unusual form, which was named helium-2. But Kapitsa showed that helium-2 indicates that it is in a macroscopic quantum state, and that helium-2 is a quantum fluid with zero entropy. Kapitsa has played a leading role in low-temperature physics for a number of decades. He established laboratories in Moscow, United Kingdom, and Cambridge. One of his associates, Lev D. Landau, was awarded the Nobel Prize in Physics for his theoretical studies on liquid helium. Low-temperature physics consists in atoms and molecules that are in constant motion. The temperature of the matter is dependent on the intensity of heat movement. When the movement is held, the temperature of the body drops to 0 point at minus 273 degrees. In Russia, Kapitsa began a series of experiments in studying liquid helium, leading to the discovery in 1937 of its superfluidity. The strongest matter under the sun, helium, colorless light gas tartless odorless, which becomes liquid in minus 269 degrees, but it doesn't like to be alone. We need to pour liquid nitrogen into the double-phase thermos. That it is also cold at minus 195 degrees. Double life of object called helium starts. This is its first phase. This warmer one. Thought both are visible at imagination cold poles. Bubble in liquid nitrogen shows that its works is boiling. Large quantities of heat are flowing out of the thermos. Liquid helium-1 becomes cooler and cooler. In the moment, it will change its phase at the second, cooler one. This is it. The word of paradox helium-2 starts from minus 271 degrees. This glass vessel has a ceramic bottom and thousands of little capillary channels in it, viewed with narrow mesh, too narrow for helium-1. It does not flow or drips because this phase has viscosity. Lambda point, minus 271 degrees, beginning of helium-2, was beginning of impossible but fact thought. Helium has become superfluid, it drips, flowing, and it will drip even though narrower ones. Minus 272.5 degrees very near to absolute zero, to the limit of possibilities and imagination, and it drifts faster and faster, because this fact have no viscosity. This is how superfluid helium-2 once first thin layer climbs up to the vessel. Then it jumps out of it and cries with helium tears. It cries because it doesn't know what it is all for. In 1965, Arno Penzias and Robert Woodrow Wilson at Bell Telephone Laboratories had built a Dick radiometer that they intend to use for radio astronomy and satellite communication experience. This object or instrument had an excess 3.5 Kelvin antenna temperature which they couldn't account for. They received a telephone call from Crawford Hill. Dick famously kept, "Boys, we have been scooped." A meeting between the Princeton and Crawford Hill groups determined that the antenna temperature was indeed due to the microwave background, so Penzias and Wilson received the 1978 Nobel Prize in Physics for their discovery of cosmic background radiation. But what is cosmic background radiation? In cosmology, cosmic microwave background is thermal radiation filling the universe almost uniformly. With a traditional optical telescope, the space between stars and galaxies, the background, is completely dark, but a sufficient-sensitive radio telescope shows a faint background glow almost exactly the same in all directions, that is not associated with any star, galaxy, or other object. The CMB's serendipitous discovery in 1964 by American radiometer astronomers Arno Penzias and Robert Woodrow. Cosmic background radiation is well explained as radiation left over from an early stage in the development of the universe, and its discovery is considered a landmark test of Big Bang model of the universe. This image was taken by COBE. It shows the temperature of the cosmic background radiation plotted in galactic coordinates, with red color, with red its color, and blue and violet hotter. This dipole anisotropy is because of the Doppler effect. Here we can see a real Doppler effect. If the Earth moves with respect to the microwave background, it will be blue shift to a higher effective temperature in the direction of the Earth's motion, and red shift to a lower effective temperature in direction opposite to the Earth's motion. And this is all. The end.